Welcome, this is video 1 for the Circuits Unit Notes. In this unit, the big ideas are 1 and 5, where objects and systems have properties such as mass and charge, and systems may have internal structure, and then changes that occur as a result of the interactions are constrained by conservation laws. So for this unit, the learning goals that you'll be graded on, I want you to be able to solve problems involving Ohm's Law. I want you to explain what happens to the voltage in a circuit. I want you to explain what happens to the current in a circuit, and I want you to be able to describe power usage of resistors in a circuit. So to get us started, we need to talk about resistance. All matter has some property of resistivity. It depends on molecular and atomic structures. So when we talk about materials, we know that they're made of atoms, and atoms have protons, neutrons, and electrons. And when it comes to electrons, well, in certain materials, the electrons can be motivated to move around, or they can be free to move around. And the degree of freedom that those electrons have will depend on the type of bonds holding atoms together. So for metals, room temperature heat is enough to cause those electrons to leave their atom. And we call those metallic bonds, where the electrons are collectively shared by all the positive ions. We call those moving electrons the sea of electrons. However, materials like glass, where there's covalent bonds holding them together, are going to keep all of their electrons closely attached to the atom. So here's a couple of diagrams here. So for here we have our metallic bonds, and we can see that there's individual free electrons from the valence electrons. They can go in and around, they can wiggle around, they can move pretty much at random. But for things like quartz and glass, the electrons are locked in a little closer to the atom. So this relative mobility of the electrons is what we call conductivity. And materials with higher electron mobility is what we call conductors. Materials with lower electron mobility will be called insulators. So here's a little graph showing this, where up here the best conductor is silver, and the worst conductor, or the best insulator, on this diagram anyways, would be rubber. In fact, there's one more. Air is an even better insulator than rubber. And I believe gold might be a better conductor than silver, but I'm not sure on that one. So while the normal motion of free electrons in a conductor is random, we can influence their direction. Remember from the last unit, we discussed electric potential, commonly called voltage. And electric potential was the potential energy per unit charge. So what we can think of as electric potential giving us then is it provides motivation. So it kind of gets the electrons to move on their own. So when we apply a voltage across a segment of wire or a segment of conductor, whatever, that voltage or that electric potential will cause the electrons to move in a certain direction. And generally they move from higher potential to lower potential. Now, something else we need to do is we need to provide a path for the electrons to follow. Typically, that's going to be a wire. And usually for wire we use copper. I know silver is a better conductor, but the price of silver is higher than the price of copper, at least for now. So we take some copper metal, we surround it with a rubber casing, that way the electrons can't jump off, and this provides a path. Now the path itself cannot have any breaks because air is a really, really good insulator and the electrons really don't want to travel through it. So if we want the electrons to move continuous, we need to have something called a circuit. And typically a circuit is something where the starting point is going to be the same as the finishing point. It's going to be a loop. So a circuit always has to complete a perfect loop. Now, this also leads us to a new concept called current. And the way we find it is by counting how many charges pass a point in a wire per second. So in this diagram right here, we can see that we have a wire that's blown up, and we're looking at a cross-sectional area, and we're counting how many of these charges pass through this point every second. So the way we calculate current, we use a capital I. We use a capital I because when scientists were first studying current, they were looking at the intensity of the electricity. So I for intensity. And this equals, it is a derivative, dq dt. So it is the derivative of charge with respect to time. So the way we will interpret that then is the change in electrical charge over time. This is not a vector, though a current does typically have a direction of sorts. Something else to consider, since this is charge over time, remember that charge is conserved. And since charge is conserved, that must mean that current must be conserved as well. So the electrical current must be conserved. That's going to play a part later on. Okay, now we can start wrapping all this together into something called Ohm's Law. So Ohm's Law gives us a way of calculating resistance of a material. It gives us a way of calculating potential difference, and it gives us a way of calculating everything else we need. So right here I have a circuit. We have our DC power supply, or some source of power. We have a current flowing through the wire, and we have a resistor. Sometimes you'll see this symbol here as the symbol for a DC power supply or DC voltage. Just a series of long and short lines where the long line is positive and the short line is negative. So this right here gives us our electrical potential difference, our voltage. So that's going to be our delta V. The current is I and the resistor is R. So what Ohm's law then tells us is delta V equals I times R. It's a very simple formula. I would argue it's one of the most important ones of our current century. So if I know what my potential difference of my DC power supply or my battery or whatever you're using, whatever that's going to be, if I know that voltage, and if I know how much current there is in my circuit, I can calculate the resistance. Or if I know the voltage and resistance, I can calculate current. Or if I know current and resistance, I can calculate the voltage. Also, this is where conservation of charge comes back in. Notice how this circuit is a complete loop. It starts on the positive side of the battery and it finishes on the negative side of the battery. So all of the current that leaves the battery returns to the battery. And that gives us our conservation of charge. and conservation of current. Now, the way we measure resistance, we measure it with a unit called the ohm, and also with current. Remember that current is charge over time. We measure current with the unit, the ampere, or amp for short. So, with our Ohm's law, the V is in volts, the I is in amps, and the R is in ohms. With the ohm, we do use the omega symbol for the symbol for ohms. Now, the purpose of a resistor is that it will convert electrical energy into thermal energy. So if you were to touch a resistor after it's been used for a while, you'd have to be careful. It might burn your hand because they do tend to get warm. Now, the rate, because we're converting one form of energy to another, well, that's power. So a 2-watt resistor will convert 2 joules of electrical energy into 2 joules of thermal energy every second. Okay, so power. We formally define power as work over time. Well, in our previous unit, remember that work, when we take a look at our equal potential lines, work was equal to the potential multiplied by the charge. So if I were moving from one equal potential line to another, I would have a delta V, potential difference. So work is equal to that potential difference times the charge. So that means that power, which is work over time, would equal my delta V times Q over T. Well, here we see we have a Q over T, which is the definition for current. So that means that power is equal to my potential difference multiplied by my current. So a resistor with a higher power rating, they tend to be physically larger. And another thing is, if you exceed the power rating of a resistor, you can melt it or catch it on fire. Okay, so using Ohm's law, delta V equals IR, and using power, delta V times I, we can algebraically put these two equations together and solve for any one of these 4 electrical properties. So notice for power then, I have 3 equations, V times I, R times I squared, V squared over R, and that's just substituting V equals IR into the power equation. For voltage, V equals I times R, so that one, or power divided by current, or the square root of power times resistance, and then so on and so forth. So this is called the electrician's wheel, and it just gives us a way of calculating all 4 of these variables. And they just use simple algebra to get all of them. Now finally, the resistance of a material can depend upon temperature. So we have 2 different types of resistors, ohmic resistors and non-ohmic resistors. So in an ohmic resistor, the resistance remains constant for a wide range of voltages and currents. So a wire, just a plain old copper wire, has resistance, and it's ohmic resistance. A carbon film resistor has, ohmic resistance. Basically, it's going to be anything that obeys Ohm's law. So if we were to make a graph of the voltage versus current, we should see a nice linear relationship. And if we take a look at delta V equals I times R, if I do delta V divided by I equals R, well, that means that the slope of this line would equal the resistance. Because if I look at this graph, rise over run, I would see I'd have my voltage divided by current. A non-ohmic resistor then is one that the resistance changes, um, and it's very, very dependent on heat or temperature. Diodes are an example, also light bulbs. Light bulbs do not obey Ohm's law very well. They do to a certain degree, but as they get hotter, it changes. So for this one, notice that if I were to make a voltage versus current graph, that the resistance changes. This looks like a parabolic relationship. It doesn't have to be parabolic, but it does change. All right, well, this concludes our video for the first video for the circuits unit.